Let us start now. On. Let us start the job. Let us start our class. Now, today, let us discuss the process of heating and humidification in adiabatic chemical dehumidification. Now, this process is generally used for industrial air conditioning and now used for some other comfort air conditioning installation requiring either a low relative humidity or low dew point temperature in the room. In this process, what is going on? The water is incoming air is passed over some chemicals, which has a tendency or affinity, which has the ability to absorb certain moistures. As the air come in contact with these chemicals, the moisture it contains in the air, it gets condensed out of the air and keeps up and absorbed by these particular chemicals. And at the process of condensation, it keeps away latent heat. Now, due to condensation, the specific humidity decreases. Due to the condensation, specific humidity with the amount of moisture present per kg of dry air decreases, and the heat of condensation thus supplies sensible heat for heating the air and thus increasing the dry bulb temperature. The process, which is the reverse of adiabatic adsorption process, is shown here by the line 1 to 2 and the psychrometric chart. The path followed by this process is along the constant vapor wet bulb temperature line or constant enthalpy line. Means enthalpy remains constant, means there is no heat transfer takes place, means there is no heat transfer takes place, and adiabatic temperature, constant adiabatic bulb temperature means this is the wet bulb temperature is saturated temperature at the time. Just 1 second. As we know that the temperature of the air recorded by thermometer when the bulb is surrounded by wet bulb is exposed to the air. Such a thermometer called wet bulb temperature, wet bulb thermometer. When the wet bulb thermometer temperature is generated by TW, is not affected by moisture. Well, this is the thermometer, it is the temperature of the surrounding, but is fully affected by the moisture itself. Now, the path followed this process is along the constant wet bulb temperature line or constant enthalpy line. The effectiveness of the efficiency of the humidifier is given as NH, actual increase in the dry bulb temperature and ideal increase in the dry bulb temperature. This is actual increase is TD3, here minus TD1, where TD3 is the it is the temperature at the point 3, and TD ideal increase in the dry bulb temperature is temperature at the point 2. Now, it is the minus the initial dry bulb, incoming dry bulb temperature. So the process is due to the condensation, the specific humidity of the incoming air decreases, and which is shown here. The specific humidity incoming air at was W1 and it is diminishes to W2 or in ideally W3. And the heat of condensation supplies the heat of condensation. It supplies the sensible heat for heating the air that increases drive-out temperature. So both the terms are going on. Due to the condensation, specific heat is decreasing, and due to the condensation, the specific heat for heating the air thus increasing is due to condensation. The sensible heat is the heat of condensation is supplies such the sensible heat of heating, thus increasing the target temperature. So condensation is doing two things. One, it is reducing the moisture content, and another is it is by supplying the due to the latent heat of condensation, it is supplying, which is it is supplying, it is increases heat content and increases the drive-out temperature of the moisture of the thermometer, which is shown here. Here, initial drive-out temperature was TD1, and later, due to concentration, it was ideally improved up to 3, or actually improved up to TD2. So here, temperature is increased, drive-out temperature of the thermometer air is increasing, and the initial specific heat means the amount of moisture present, specific humidity, amount of moisture present in the air per kg of drive-out temperature minus is equal to minus W2. It is increasing. It is also decreasing due to the moisturization, due to demoisturization. The effectiveness and efficiency of the thermometer generally is given as actual increase in drive-out temperature, which is the TD3 minus TD1, and ideal increase of the drive-out temperature, that is TD2 minus TD1. So it will reduce to up to the 0.3 if it is ideally, it is actually considered, and reduce to 0.2 which is ideally considered. The process is accompanied ideal process, actual process performed is actually the accompanied release of latent heat called heat of absorption. Release of heat called heat of absorption, which is very large. Thus, sensible heat retain of the air, it exceeds the loss of latent heat, and the process shown above the constant wet bulb temperature line. Two types of chemicals used for dehumidification are absorbent and now there are two kinds of chemicals used for dehumidification. The absorbents are substance which can take up moisture from air, and during this process we can substance which can take up the moisture from air, and thus during the process change it chemically, physically, and both aspects. This includes water solutions or brines or chemical chloride, calcium chloride, lithium chloride, lithium bromide, ethyl glycol. Here, so water solution or brines of calcium chloride, or the water solution or the brines or calcium chloride, lithium bromide, lithium ethyl glycol. These are used as air dehydrators by spraying or otherwise exposing a large surface of the solution in the airstream. So it is air dehydrating. It is dehydrating. It is reducing the moisture content, or by spraying itself or otherwise exposing a large surface of solution in the airstream. So either spraying it in the airstream or exposing a large solution of the large surface of solution in the airstream, which actually absorbs the moisture. The absorbents are substances in the solid state which take up moisture from air, and during the process does not change it chemically. This includes silica gel and activated alumina, which is a form of silicon dioxide prepared by mixing fused sodium silicate and sulfuric acid, and activated alumina, which is a porous amorphous form of aluminum oxide. So what we get, first of all, there are two different types of dehumidification process with two different absorbents. Sometimes absorbents are substance which takes up moistures. One type of absorbent, or one type of absorbents takes are substances which takes up moisture from air during the process and change it chemically, which takes up moisture and from the process and change it chemically, physically, and both aspects. Now, they are generally the water solution or brines of different type of salts like calcium chloride, lithium chloride, etc. Now, they are used as water bipyrite by spraying or exposing to a large surface of the solution of the stream. The absorbents are generally substance in the solid state which can take up moisture from the air during the process and does not change chemically or physically. This includes silica gel. This was a water solution or brine type. But next, another type of observations are available which are in the solid state. Say silica gel, which is in a form of silicon dioxide prepared by mixing fused sodium silicate and sulfuric acid. This is silicon gel. Activated aluminium, which is a porous amorphous form of aluminum oxide. Next, let us go for the sample set problem. The saturated air at 21 degrees centigrade is now passed through a dryer so that its final relative humidity is 20 degrees centigrade. The dryer used silica gel absorbent. The air then passes through a cooler until next air is passes through a cooler and its final temperature is 28 degrees centigrade without a change of specific humidity. Determine the temperature of air at the end of the drying process, the heat rejected during the cooling process, the relative humidity at the end of the cooling process, and the dew point temperature at the end of the drying process. Then the moisture removed from the entirely drying process. So what is given here? It is the temperature TD1, saturated air of the incoming air. So what is given here? It is TD1. That is TD1 is 21 degrees centigrade. TD1. It is first given here. It is passed through a dryer so that final relative temperature becomes 22. But its relative humidity is not 22, but something more than that. So it is first of all, mark the initial condition. So 21 degree diagonal sensor up to the saturation curve. Here up to we have drawn this vertical line from 20 degrees centigrade up to the saturation curve, which is the 0.1, which is because air is fully saturated. Passed through a dryer, the initial here passed through a dryer temperature. Yes, it is given that air is fully saturated air at 21 degrees centigrade. So it is reached from 20, it is up to 0.1 will be on the saturation curve line. Now, saturation curve line or wait for temperature line, where it is fully saturated. Now, since the drying process is a chemical dehydration process, therefore it follows a path along the constant well bulb temperature or the constant enthalpy line. Means air enthalpy is constant. In drying process, chemical dehydration process, it is follows a path along the constant wet bulb temperature or the constant enthalpy line. This is the wet bulb temperature line and the constant enthalpy line in the as shown in the figure 1 to 2. Now, the point 2 is to be marked at relative humidity line over 20%. This is point 2. So there is 2 points. First of all, the air is saturated. So at the diagonal temperature given, that's 25 degrees centigrade. The point 1 is on the saturated vapor line, saturation curve or saturated vapor line. And saturation curve or saturated vapor line where air is saturated. Next, this point is the after the cooling, as dry silica gel will absorbent, dry silica gel, air reaches final temperature that's different, but it is cooled and it is dehumidified up to from saturation temperature to a 20 degree 20% relative humidity line. Now, since the drying process of the chemical Liberty coefficient, this follows a path along constant well bulb temperature, means and the constant enthalpy line, means well bulb temperature or saturation well temperature remains constant here, and thus it reaches the point 2, and where this intersect at the relative melting line. From the psychrometric chart, the temperature at the end of drying process is at point 2, or is TD2, is 38.5 degrees centigrade. Temperature at the end of the drying process is at point 2, that is 38.5 degrees centigrade. It is TD2. The cooling process is shown by the line 2, 3 on the psychrometric chart. The temperature at the end of drying process is given is if we drop a vertical, it will become the dry bulb temperature at the end of drying, which is equal to 38.5 degrees centigrade from the psychrometric chart. The cooling process is now shown by the line 2, 3 in the psychrometric chart. From the psychrometric chart, we find that enthalpy of the air at point 2 is given as H1 is equal to H2, 61 kilojoule per kg, and enthalpy air at point 3, which is also a vertical over the enthalpy line, which is given as a point, which is equal to H3. Next question is how you get the point 3 point. So if heat rejected during the cooling process, is given as H2 minus H1 is equal to 18 kilojoule per kg. So what we know here, how we will know the point 3? We know after the cooling, the temperature becomes TD. After the cooling, dry bulb temperature remains same. So here it is 21, and it is the point 3 here. Now the relativity at the end of the cooling process, the chart here is 5.3 on the is given as 0.3, so 5.3 is equal to 55%. From the psychrometric chart, we find that the dew point temperature at the end of the drying process is TB2, and the dew point temperature at the end of the drying process is TDP2 11.6, and that is TB2. Now, if we draw this horizontal line up to the saturation curve, so at the end, the saturation point or the dew point temperature will be at the end of, and will be masked here, and it will be given from this point, will available from this point here, which is given here as 11.6 degrees centigrade. From the psychrometric chart, we know what is W1. W1 is given as 0.017 and W2 is given as the 0.0084 kg per kg of dry air. So moisture removed during this drying process is W1 minus W2 into is equal to 0.157 to 0.0084 is equal to 0.0073 kg per kg of dry air. Next comes another problem. This problem number 28. What we are getting here, the 300 cubic meter of dry air is supplied per minute from outdoor condition of 40 degrees centigrade dry bulb temperature and 26 degrees centigrade wet bulb temperature. Wet bulb temperature to an air conditioned room. The air is dignified first by the cooling coil having bypass temperature 0.32. They are first dignified by a cooling coil, then having the bypass temperature equal to হ্যাঁ, না কেন? হ্যাঁ, ঢুকে পড়ো, ঢুকে পড়ো। The 300 millimeter of dry air is supplied per minute from output condition of 40 degrees centigrade dry bulb temperature and 26-degree wet bulb temperature to an air conditioned room. The air is dehumidified first by a cooling coil having the bypass factor 0.32 and the dew point temperature is 15 degrees centigrade, then by a chemical dehumidification. So first it is dehumidified by a cooling coil, then by a chemical dehumidification. The air leaves the chemical dehumidified at 30 degrees centigrade dry bulb temperature. Air is then passed over a cooling coil whose temperature, surface temperature is 15 degrees centigrade and bypass factor is 26. Calculate the capacities of two cooling coils and humidifier. Calculate the capacity of the two cooling coils and humidifier. Now what is given? V1 is the velocity of the volume of the incoming air, 300 cubic meter per minute. TD1 is 40 degrees centigrade. TD1 is 40 degrees centigrade. Dry bulb temperature of the incoming air. The wet bulb temperature of the incoming air is 26 degrees centigrade. Aperture dew point is 15 degrees centigrade and dew point at number 4 is 40 degrees centigrade. Is 30 degrees centigrade. Where is air leaves the chemical dehumidifier at 30 degrees centigrade dry bulb temperature. This process involves in air conditioning a room shown in this here. First of all, the outdoor condition of air at 40 degrees centigrade dry bulb temperature, 26 degrees centigrade wet bulb temperature, and the psychrometric chart. Let us mark it at 0.1, which is given here. This is the 0.1, which is 40 degrees centigrade dry bulb temperature and 26 degrees centigrade wet bulb temperature. If we drop a particle from both these points, it will intersect at the 0.1 and we'll get the required point. Now, this is 0.1 we have achieved. Now we have to mark the 0.2 on the saturation curve representing the aperture dew point. That is, aperture dew point is 15 degrees centigrade of the cooling coil. So aperture dew point we have to mark on the saturation curve. That is 15 degrees centigrade of the cooling coil. That is, aperture dew point is marked here at it is 30 degrees centigrade and the cooling coil. Just 1 second. 15 degrees of the cooling coil. Now, that is the 15 degrees centigrade. We have to mark it from here, and if the vertical is reached, it will reach here. This is the point, aperture dew point, that is 0.2 here. So 1 is there, the 0.2 is here. Next, what we are getting. Next, since the bypass factor of the cooling coil is 0.32, that mark 0.3 on the, so that the bypass factor of the cooling coil is 0.32. It is then the mark 0.3 on the line 1, 2, so that length of the line 2, 3 is equal to 0.23, the length of the line 2, 1. So we have to write the 0.3 and length, it is to be line 2, 3 should be around 32% of the line 2, 1. So bypass factor means this is the amount of temperatures being cooled. So this is the percentage of temperature. So we are checking that this is the point number 3 on the actually what is going on. If it is the fully efficient air conditioning system, then full cooling is possible. But actually, it never happens. That is when the cooling decooler or cooling coil cools only a particular amount of, only a certain percentage of cooling, not the 100%. That percentage is around 0.32% or 0.32 of the total cooling effect. So we have to make the 0.3 here to make the by running 0.02 or 0.32 of the length of the line to 3. The 0.3 represents the condition of air, leaving the cooling coil. This air passes through a chemical dehumidifier. This air now passes through a chemical dehumidifier. From 0.3, draw a constant enthalpy line to intersect the vertical line drawn through 30 degrees centigrade dry-bulb temperature. Draw a constant enthalpy line from 0.3 to intersect the vertical line through 30 degrees centigrade dry-bulb temperature at 0.4. So this is the 0.4, and we have dropped a, this is the 30 degrees centigrade dry-bulb temperature, this is the 0.4 here, and we also drop a particle and constant enthalpy line from through 0.3 and which intersect at 0.4 here. Then the air leaving the chemical dehumidifier passes over another cooling coil having surface of equal to 15 degrees centigrade. And through 0.3, draw a horizontal line, intersect the vertical line through the 15 degrees centigrade DBT, dry-bulb temperature. So here we are drawing, this is the 15 centigrade line, and so we are running a horizontal line here to meet the point at equal to 0.5. Since the bypass factor of this coil is only 0.26, then the mark 0.6 on the line for 5, so that length of the line 5.6 is equal to 0.63 into the length of the line 5.4. Thus, the 0.6 represents the condition of air leaving the second cooling coil. So 5.6 will be only, point number 6 will be only 25% of the total coil. And thus we are getting the temperature of that particular dry-bulb temperature at that point also from the psychrometric chart. So what is the capacity of the cooling coil? Capacity of the two cooling coils. From the psychrometric chart, the specific humidity or the amount of moisture present of the incoming air at point 1 is given as W1 0.0156 kg per kg of dry air. That is W1 here, which is given here. And enthalpy at the point 1 is given as H1 is 80.6 kilojoule per kg of dry air. Enthalpy of point at air at point 1 is H1 80.6 kilojoule per kg of dry air. This is the H1 here. It is given on the enthalpy line if you drop a vertical from point 1 to the enthalpy line. That is 80.6. The specific volume of air at point 1 is also available from the specific volume of air at point 1 is also available from the psychrometric chart is equal to VS1 is 0.94 cubic meter per kg. So enthalpy at the point 3 is available. Enthalpy at point 3 by dropping a vertical to the enthalpy line, at point 4 dropping a vertical. Enthalpy line is 54.5 kilojoule per kg. And H4 is H3 is also equal to 54.5. The specific humidity of air at point 4, W4, by drawing a horizontal line is equal to 0.094 kilojoule per kg of dry air. The enthalpy of air at point 6 is H6. We are not getting all these point enthalpies in the similar manner by dropping the vertical on the vertical line. That is H3. H6 is kilojoule, and the mass of air thus supplied is V1 by VOC. VOC is 300 kilojoule, and specific specific volume is given as VS1. So mass of air supplied is 9.13 kilojoule per kg. So the capacity of the first cooling coil, H1 minus H3 multiplied by the mass of air supplied, which is given as 8326 kilojoule per minute. And the second cooling coil is also H4 minus H6 into mass of the air, that is 319, 54.5 minus 43, 366.8 kilojoule per kg. Thus, what we are getting, the capacity of the humidifier, we know that the capacity of the humidifier is MA W1 minus W4 to 319 to 015 is equal to 0094 with 1.98 kilojoule per kg. The adiabatic mixing of two streams through acids. When two quantities of air having different enthalpies and different specific humidities, when two quantities of air having different enthalpies or different specific humidities are mixed, the final condition of the air mixture depends on the masses involved, and on the enthalpy and specific humidity of each of the constituents masses which enter the mixture. Now consider two airstream 1 and 2 mixed adiabatically as in the figure A. This is with the mass, enthalpy and specific humidity M1, H1, H2, W2, M2, H2, W2, and it becomes M3, H3, W3. The M1 is the mass of air entering at 1, H1 is that of the air entering at 1, W1 specific humidity of the air entering at 1. Similarly, H2 are same. H2 and M2, H2, W2 and M3, H3, W3 are same. Assuming no loss of enthalpy and specific humidity during the air mixing process, we have for the mass balance M1 plus M2 is equal to M3. For the energy balance, M1 is into H1 plus M2 into H2, M3 into H3. And for the mass balance of water vapor, so mass becomes the addition of the two masses, M1 plus M2 is equal to M3. And for the energy balance, M1 H1 plus M2 H2 is equal to M3 H3. The energy balance, the addition incoming air energy, mass into enthalpy per kg, mass into enthalpy per kg is equal to the mass into the outgoing out. So mass balance of the water vapor, mass multiplied by the specific humidity, mass plus mass multiplied by specific humidity is equal to mass multiplied by specific humidity outlet. Now substituting M3 from equation to 3 means from this equation to this equation. So this equation will involve the same H3, M1 H3, M2 H3, or M1 H1 minus M1 H3 is M2 H3 minus M2 H3. So M1 by M2 is H3 minus H2 divided by H1 minus H3. Substitute the values of M3. Next, in equation 3, we'll have M1 by M2 is W3 minus W2 divided by W1 minus W2. Then equation, from the equation, both this equation, 4 and 5, if you equate the M1 and M2, H3 minus H2 equal to W3 minus W2, H1 minus H3, W3 minus W3. The adiabatic mixing process is represented on the psychrometric chart as in figure here. The final condition of the mixture point, final condition of the mixture point 3 lies on the straight line 1 to 2. The point 3 divided the line 1 to 2 in the inverse ratio of the mixing masses. By calculating the value of W3 from W equation and from point 3 is plotted for the line 1, 2. Calculate W3 and then we plot it from the line 3. It may be noted that. So what we are doing, first we have to calculate the W3 here by knowing the mass of 1 and 2 and the specific humidity of 1 and 2. From this, we will get the W3 and we put it here. Then the fog region which is telling that the warm and high humidity air is mixed with cold air. When the warm and high humidity of air is mixed with cold air, the resulting mixture will be a fog. And the final condition is 0.3 on the psychrometric chart, which will lie to the left or above the saturation curve, which represents the fog region. The temperature of the fog is that of the extended waveguide temperature passing through the point. So what they are saying, if you got the point on the psychrometric chart, we lie to the left and above the saturation curve. Either it is shown here, this is either left as well as above the saturation curve, we represent a fog region. The temperature of the fog is that of the extended waveguide line passing through point 3. This fog may also result when temperate stream or a very fine water spray is injected into air in a greater quantity than required to saturate the air. Even lesser quantity of stream, if not mixed properly, may be result in a fog. The fog can be cleared by heating the fog, mixing the fog with warm and unsaturated air, or mechanically separating the water diplet from the air. Let us go to the problem 6.29. Now, 1 kg of air at 40 degrees centigrade, dry bulb temperature, 50% relative humidity is thus mixed with 2 kg of air at 20 degrees centigrade, dry bulb temperature, and 20 degrees centigrade dew point temperature. Now, calculate the temperature and specific humidity of the moisture. 1 kg of dry air, 40 degree DBV, and 50% dry bulb temperature in relative humidity is mixed with 2 kg of air at 2%, 20% dry bulb temperature, 20% dew point temperature. Calculate the temperature of the specific into the mixture. So, what is M1 here? The mixture number 1. Here, M1 is 40 degrees centigrade dry bulb temperature, is 40 degrees centigrade here, and 50% relative humidity. Relative humidity line is 50%. It is joining this point here. That is W1.1. The specific W1 is available from here. And the fixture number 2, we have 20 degrees centigrade dry bulb temperature, which we have it, and it is 20% dew point temperature, 20 degrees centigrade dew point temperature. So, dry bulb temperature, dew point temperature, same means this is acting on the saturated line 2, saturation curve 2. So, this is the point 2 here. Then M1 is given as 1 kg, and phi 1 is also known to us. And now let us do the specific humidity of the mixture, W3, which is available from here. Now, let the condition of first mass of air and it is marked on the psychrometric line at point W1. Now, mark the condition second mass of air at 20% dry bulb temperature, means at point 2, as shown in the figure. This point lies on the saturation curve. Join this now, point 1 and 2 here, and from the submit chart, we find the specifically first mass is given here, W1, that to the second mass is given as W2. So we want to know M1 and M1 divided by M2 is equal to W3 minus W2 divided by W1 minus W3, which is M1 by M2 is given as M1 is equal to 1 kg and M2 is given as 2 kg. And W3 is unknown to us, and W2 is just got here from 0.0148, and W1 is got from 0.0238, 0.0238 is equal to W2. So if we put this value, we get the only one unknown W3, which is can be calculated as W3 0.0178. Now plot 3 on the line joining point and 2. We got the point. We have to point the point 3 on the line joining corresponding to the relative specific humidity W3. Now we find that the point 3 dry bulb temperature is given. If we drop a vertical to the dry bulb temperature line, we'll get 26.8 here. 26.8 degrees centigrade. Okay, we are stopping this one here.